All right, we're going to continue on chapter 7. We have covered a lot of things this chapter. We've talked about what alkyl halides are. We've talked about what a good leaving group is. And y'all might recall that a good leaving group is a weak base. A weak base is the conjugate base of a strong acid, which is why alkyl halides work really good for these sorts of reactions. We jumped into SN2 reactions, which, if you were to ask me, Morris, what's the easiest reaction of this chapter? I would have to say SN2. SN2, all you do is swap a group from another. It's a very simple mechanism, concerted, one step. The only thing you got to watch out for is is there a lot of clutter around the electrophilic carbon? If there's not, you just add the group. If there is, it probably won't work. If you're secondary, make sure to do that inversion of configuration. Okay? Then Dr. Hathaway took the reins and taught y'all E2. If you were to ask me what's the hardest reaction of this chapter, I'd have to say bimolecular elimination. There's a lot to consider. You pluck off a beta hydrogen, you form a new pi bond, you kick off a leaving group. It is concerted. There is a requirement that there's an anti-relationship between the hydrogen and the leaving group, which is usually not a problem, except for whenever you have two stereocenters next to each other, and you might have to draw a Newman projection to figure out which alkene is formed. There was two competing alkene products. If you're using a small base, you're going to be trying to form what's called the Zaitsev alkene, right? The Zaitsev alkene is the more substituted alkene. If you're using a huge base, which is usually potassium tert butoxide, KOTBU, that's going to favor the Hoffman alkene, where you pluck off the most accessible hydrogen. Then last class period, we talked about unimolecular reactions, SN1 and E1. Now for the first door prize of the day, I've been telling you, don't look at your notes, you cheaters. What is the most important thing you should be asking yourself with unimolecular reactions? What about it?
If they're more stable, which one's more stable?
Yeah, very good. Very good. So when you see a unimolecular reaction, the very first thing you need to be asking yourself is, can I form a stable carbocation? And I talked about tricks. You're already adding the sticker. That is amazing. Ladies and gentlemen, she does not wait. She just goes for it. All right, so can I form a stable carbocation? There were some considerations, right? One consideration is hyperconjugation, right? Tertiary alkyl halide is going to form a better carbocation than a secondary. What about resonance? That was another one, wasn't it? Can my carbocation form a good resonance structure such as allyl or benzylic? We're going to learn solvent also plays a role in this, but the question you got to ask yourself is, can I form a stable carbocation? Because that is the bottleneck of the rate. Rate's dependent on one thing, and that's the substrate, because the substrate's the thing forming a carbocation. Then I kind of introduced this whole carbocation rearrangement thing, because if you can ask the question Sarah just told me, can I form a stable carbocation? Then the immediate next question should be, what? What's the next question you should ask after can I form a stable carbocation? What'd you say? Say it louder. Can it rearrange? Can it rearrange? That is a great question, because I will try to trick you on that at least once on the test. You're going to see it, you're going to form that carbocation, and then you're going to just write the answer. And if you forgot to rearrange it, if it can rearrange, you just lost some points, right? So go slow, take your time on this test whenever it's given. And just know the universe is lazy, and if it can form something more stable, it's going to do it. Not same stability, so it won't go from a secondary carbocation to another secondary, generally speaking. But if it can go from a secondary to a tertiary or secondary to an allylic, it's going to do the swap. There's two types of carbocation rearrangements I introduced to you. One was a methyl shift and one was a hydride shift. Which one takes priority if possible? Methyl. It's like a little bitty shift. But wait, what'd you say? Methyl? Methyl does not take priority. Hydrogen. I heard hydrogen in my head. I don't know why. Hydrogen, size of a marble, it's just gonna hop right over. Methyl, a little bit, clunkier. It can do a methyl shift, but if hydride shift can occur instead, it's gonna prefer that one. So let's do one quick problem just to address the whole carbocation rearrangement issue. In fact, let's do this. Yes, I have a funky looking molecule that I just drew, but at the end of the day, can we all agree it's just an alkyl halide? It's just the R group is a little complicated, right? And we should be at the point where you can look at those reaction conditions and tell me what kind of reaction is going on. Anybody want to take a crack at it? It's 1 of 4, 25% chance. How about this? Teamwork makes the dream work. What digit goes with it, 1 or a 2? It's a 1, good job. All right, does it start with an SN or an E? SN, it's an SN1 reaction, good job. Actually, I said teamwork and you did it all. Good. This is SN1. Why is it not elimination?
There's
No heat. Why is it not, SN2? Okay. Why is it not SN2? This is a label your tubes one. You wouldn't want that on your water bottle. Going once, going twice. All right. It's not a strong nucleophile, is it? Methanol is a weak nucleophile. Do you see a negative charge on methanol? If it was OMe negative, then it could be SN2-ish. But because it's just like a mediocre nucleophile at best, a weak nucleophile, it's not going to go SN2. Because SN2 requires a strong nucleophile. If you remember the rate equation, rate's dependent on the concentration of substrate times the nucleophile. SN1, the strength of the nucleophile, doesn't matter. So yes, this is SN1. Going back to what Sarah charged the class, what's the first question you should ask if you determine it's SN1? Can I form a stable carbocation? I discourage you from just using your imagination. Draw the actual carbocation, okay? Take the time. Say, okay, it's SN1. Can it form a stable carbocation? So I would draw the actual carbocation. Loss of leave-in group according to the mechanism. Realized I just drew a little puppy dog. You see the tail? Mm-hmm. Yeah. Old Rover. What kind of carbocation is that? Primary, secondary, tertiary alkyl, primary, secondary, tertiary allyl, or primary, secondary, tertiary benzyl? Can't get more than one prize, sorry. Reagan?
This is a tertiary alkyl.
Close.
Tertiary benzyl.
Not as close.
Secondary.
Secondary what?
Benzyl.
Nope. Okay, we'll try again. No, I love this. No. I love this. No, y'all are talking. No, this is good. This is good because I'm getting feedback. That's what I need. What is alkyl? What does alkyl mean? Just a hydrocarbon, right? What does allel mean? It means on the carbon alpha to a pi bond, or an alkene. And so allel would be like this. See that? Alkyl would be something like this. It's just a carbocation of an alkane. And then benzyl would be alpha to a benzene ring. See that? You have to know that kind of distinction by heart, okay? So, can I ask again, what kind of carbocation are we looking at here? Secondary alkyl. Secondary alkyl. Reagan, you almost had it. You said tertiary, didn't you? So if you look at this carbocation, you have an R group here and an R group here, which is why that's why it's secondary. Secondary means two, pretty much. So two things attached to that carbocation. I'll tell you this, secondary alkyl is not a slouch, okay? It can do an SN1 reaction just fine. It can actually do an SN2 reaction just fine. Which is why, like on the test, when you get a secondary alkyl, you gotta know a little bit more information to discern if it's gonna go SN2 or E2. Sorry, SN2 or SN1. If it's SN1, you're also gonna see a really good nucleophile, okay? But this one doesn't have a good nucleophile, so you know it's SN1. Sorry, SN2 has a good nucleophile. SN1, weak nucleophile. Now the question is can I shift things around? Can I make this one better? Remember that was the follow-up question? Let me teach you a quick trick. If you're kind of slow at figuring out the carbocation rearrangement stuff, you should quickly say, okay, that secondary alkyl, that's not a terrible one. But if you wanted to take one of these hydrides and move it over, realize that the result would be, I'm just going to write pH for phenyl. Do y'all see what just happened? The hydride hopped over one carbon, but the carbocation went to where the hydride was. Do y'all see that? It just flip-flopped. You might be able to actually do that in your head. Do y'all see that I just wasted my time doing that? Because I went from secondary alkyl to a what? Primary alkyl. So that's like a no-go. We're not going to do that. So right now we know that this is the winner. And as you practice this, you'll realize I'm not even going to consider doing the one Morris just showed me. Okay? But then you're like, well, there's no other places to shift, Dr. Morris. Well, there is. Because I realized that right here, there's no hydrides, are there? Can methyls shift? Methyls can shift. Now what happens if one of my methyls hops over here and does a shift? We'll call it a 1,2 methyl shift. And while you're drawing that, I want you to just note that hydride shifts are a little easier because whenever you move a hydrogen, you don't have to show it in either case, do you? Because they can be implied. But methyls can't be implied, so this actually fundamentally changed the carbon skeleton of your structure. Do you see that this carbon right here has one methyl, and this carbon now has two methyls? It's because one hopped over. And this one had two methyls, and now it only has one. I heard somebody say tertiary. Tertiary what? Benzyl. Good. Tertiary benzylic. Good. Because you're alpha to a benzene ring. This is tertiary benzylic. Which one's better, class? Okay, there's a lot of resonance to keep that carbocation very happy. And so you have to do this carbocation rearrangement. Now methanol can come in and do its nucleophilic attack. Yes, it's irritating. Methanol has an OH on it. When you attack, the OH is still there. So now your oxygen has 3 bonds. It needs to be deprotonated. So then methanol, the solvent, remember this is solvolysis, right? Can go and deprotonate it to give you the final product. Carbocation rearrangements, aren't they fun, class? I think they're great. So this would be the final product I would expect you to draw on the test if asked for the expected major organic product. Usually on tests I tell you to omit all byproducts so you wouldn't have to really draw the MEOH2 plus. Any questions on that example? This takes practice, okay? Takes practice. Let me point something really quickly out to you as well about SN1 reactions. Suppose I had this substrate right here. Any question?
Yeah, I was just gonna ask if you could go up real fast. I mean,
Okay.
yeah, thank you.
Okay. So this bottom example that I'm going to do really quick with y'all is a super interesting example because I drew my alkyl halide on a stereocenter, didn't I? It's a chiral carbon. And you might recall that if this was like an SN2 process, you would expect some inversion of configuration to go on, right? But this is not an SN2 process. This is clearly SN1 because you have yourself a weak nucleophile and no heat. This is also one of those things that are going to irritate you on the test, especially if I don't give you multiple choice and I ask you to draw the product. Because the first question you should always ask is, can I form a stable carbocation? And I'll just go ahead and say this and put me on record. You might not even know what a stable carbocation is, and here's what I would tell you. If it's any type of allylic and any type of benzylic, those are stable, okay? Stable enough to do these. If it's a tertiary alkyl, it's good enough to do an SN1. If it's a secondary alkyl, it can do an SN1, but very slowly. If it's a primary alkyl, don't even think about it, okay? So you would never, an SN1 reaction would not work if that was my substrate. Because it would never form the carbocation to begin with. It maybe could if that was your substrate, It certainly could if that was your substrate. It really, really, really would if that was your substrate. You see what I mean? Going back to the example at hand, what kind of carbocation did I just form here? Sorry, I can't do that. That looks like an alkene, doesn't it? Here. What kind of carbocation is that? Secondary allyl. So close. Yeah, we are alpha to an alkene, so your secondary allyl. Is that a good one? Is that a good one? Allyl's pretty good, right? Can it rearrange? Really? How so? Oh, it can do a resonance structure. Yeah, it could do resonance, but even if you did resonance, your double bond would be there, and then a plus charge here, which is primary. So it's going to prefer to be in that particular resonance form. But is there any hydride or methyl shift that can happen that would be beneficial? Would a plus charge right here help you at all? That's primary. And don't ever think about putting a carbocation where a pi bond is. That's called a vinyl carbocation. Those are really bad. They don't form. So this carbocation will not rearrange. It's pretty stuck. But did y'all notice what just happened to my stereocenter? I mean, I had a good stereocenter here. It looks like it's R in its absolute configuration. But when you lost the carbocation, what happened? Did it become trigonal planar? You see that? It went from tetrahedral in R to flat. So you just lost all stereochemical information. It can't just reconvert back to R because you want it to. Chemically speaking, now it's flat. So if SN2 is like you have a chiral stereocenter and it hits from the back side, sorry, it's more like that, and it hits from the back side and does the flip like an umbrella. This one is not chiral anymore and it's intermediate. It is flat. And do you think a nucleophile will have any preference for hitting my palm versus the back of my hand? It's going to hit it both equally well, won't it? And so what's really interesting about SN1 is even if you started with a chiral starting material, the product is always going to be racemic because the intermediate is trigonal planar and the nucleophile methanol could hit from the front face or the back face. And so your final product needs to lack stereochemical information. See that? And if you don't like that, just wait for epoxide ring openings in OChem 2. They're a blast. You know, an unnamed individual, Reagan, put something on my office door, and it said, how my brain feels after an OChem test. And obviously that is indicating strain, right? Which I think is clever. But what an epoxide is actually a cyclic 3-membered ether. And doesn't that just make you mad? I've been telling you all this time, watch out for 3-membered rings, and then I go on and make an ether out of it. And what you'll be doing in OChem 2 is I might put a stereocenter here, and then you'll be doing SN2 attacks on that, even like carb anions. The question is did that just do an inversion of configuration? Yes, it did. You see what I mean? And you'll have to play around with those in OChem 2. Again, I highly encourage you to take the class. I think registration's coming up soon. Best class on campus. I endorse it, okay? Don't plan on getting any sleep, however, when you take it. I've had students say, well, is OChem 2 just like this chapter 7 stuff where it's like, oh my goodness, you have to consider the substrate, the solvent, the nucleophile. If it's a base, is it heated? Is it not? No, it's really, this is the only time it's ever going to feel like it does to y'all right now. Organic 2 is going to be more like, here's 3 or 4, or even 5 reactions in one class period, and we spend very little time, wringing it out to bleed out every detail, okay? These, as an introduction, we give you every single detail, okay? Which is why it might feel a little overwhelming. Okay, What I encourage y'all to do, because I didn't actually go over these, is these would make for good practice problems for rearrangement. See if you can get what the practice problem suggests as you try it yourself, okay? I do want to point out, in case it was not stated, I'll state it again. Sometimes you will see the word heat written. Other times you'll just see a triangle, which is the delta symbol. Delta in my class means heat, okay? Not just my class. I say that because I'm looking at, in biochemistry, we use delta notation to describe fatty acids. It doesn't mean heat in that class. In this class, it means heat. Let's talk about solvents, a riveting subject. So, in laboratory, we've been dealing with solvents, and especially as we do chromatography techniques and extraction techniques, you've been hearing the words like polar and nonpolar, haven't you? And so what does nonpolar mean? What does nonpolar mean? Jackson?
Non-polar is when it doesn't have a consistent dipole moment.
Very good. No net dipole moment. And so therefore a polar solvent would have a net dipole moment. So acetone's polar, ethyl acetate is polar. And really these reactions don't work well with nonpolar solvents. And the reason is alkyl halides are polar, aren't they? They have a net dipole, and we already learned like dissolves like. So you can't stick a polar substrate in a nonpolar solvent and expect it to go in. But here's something really fascinating. There's actually two types of polar solvents. One's called polar protic, and the other's called polar aprotic, or not protic, right? And what they found is that SN2 reactions work best in polar aprotic solvents, but SN1 and E1 work best in polar protic. What does polar protic mean? Well, the answer's right here. A solvent capable of hydrogen bonding. What have all my substrates been so far with SN1? What type of functional group? Every SN1 reaction I've given you in this class. What's the nucleophile? Did we forget our functional groups class? Alcohol. They've all been alcohols, haven't they? Do alcohols hydrogen bond? Remember H to N, O, or F kind of thing? Yes, alcohols, like water, hydrogen bond. And so does it make sense that I would use alcohols in SN1 reactions if SN1 reactions like polar protic solvents or solvents capable of hydrogen bonding? Now, I'm not going to tell you on the test, like, by the way, this is the polar protic solvent. You need to know, but I'm not going to have you necessarily memorize a list. I'll give you a trick. If a solvent has an OH on it or an NH on it, it's going to be good for SN1 or E1. That would include alcohols, carboxylic acids, ammonia, amines, carboxylic acids. Those are good polar protic solvents. It's not to say that SN1 doesn't work with polar aprotic. They can. It's just preferable you have a polar protic. And it's not to say that SN2 doesn't work in polar protic. It does. It's just not as good. And so if you're planning out a reaction and you're like, I really need to do this SN1, chances are you have best success if you run it in a polar protic solvent. If you say, I really need this SN2 to work, chances are you better choose a polar aprotic solvent if you want it to work. But look at what happens. Here's an SN2 reaction right here. If you have methyl iodide and you run it with a nucleophile at room temperature to do the substitution reaction, if you run it in methanol, which is methanol polar protic, does it hydrogen bond? that would be incompatible, really. Not really incompatible, but it would not let SN2 reactions go very fast. Notice the rate is a measly 43. It's a relative rate. But if you did it in something called DMF, in dimethylformamide, which that is polar aprotic, look at the rate now, 6,500. You really sped that reaction up now, didn't you? 150 time rate increase. If you did the same thing with different nucleophiles, you actually notice that fluorine is the worst nucleophile in polar protic, but it's the best nucleophile in polar aprotic. It's time to figure out what's really going on, okay? Here's what's going on. What is the most important thing to ask yourself with SN1 reactions? SN1, she said it earlier.
Carbocation.
Can I form a stable carbocation? What do y'all think hydrogen bonding does to carbocations?
Makes it more stable.
Mm-hmm. Because of the dipole moment and hydrogen bonding capabilities of alcohols and amines, you can actually help stabilize that carbocation as it's formed by the solvent. So not only can you do hyperconjugation and not only can you do resonance, but if you're sitting in a solvent that, man, like, I don't want to become a carbocation, but I'm swimming in a solvent that makes it a little bit better, right? It's going to let that carbocation be encouraged to form and hang around long enough to be attacked. Okay? And so you want it to kind of help the carbocation to form. Polar aprotic solvents don't destroy carbocations, they just don't help it. They're not doing anything to help that carbocation. But what's going on with the fluorine? Why is fluorine such a bad nucleophile in polar protic, but such a good nucleophile in polar aprotic? To answer this, you got to know what's the most important thing about SN2 reactions. Can my nucleophile attack? That's the most important thing. Now, can we like all look at the periodic table and discern that fluorine is a tiny little thing, and as you go down the halogen column, it gets bigger? So fluorine's this itty bitty little thing. Do you think that like a little bitty thing can hit a nucleophile or an electrophilic carbon really easily? Think about it. Think about a football field, and you have these defensive linemen. They're enormous creatures, and you have to break through them. Won't it be easier if they're spaced out to slide in as a little person and get in between them? I think so. If your goal is to go to the end zone, you can slide between those linemen pretty easy if you're a really small person. And so fluorine is really good as long as nothing is hindering it. Even if you had a kind of a cluttered, you have two methyl groups there, a little fluorine can sneak in pretty easily and do the SN2 attack, right? And iodine being really big is going to be much slower, because isn't it harder for a big person to break through with little space open? But notice the trend is flip-flopped in the polar protic solvent. Notice in polar protic, iodine is the best and fluorine is the worst. Well, what's going on? Well, now instead of my football analogy, it's not just about like, can I slide through space? Because with polar protic, what's happening is the solvent is kind of slowing the nucleophile down. Now tell me this. If you had little bitty fluorine or a little person and you made them run through a swamp or quicksand, do you think they're going to run very fast, or do you think the quicksand's going to stop them really quickly? But if you had a big, large person, don't you think the momentum's going to carry them through and overcome that force? So it's kind of like that. Think of fluorine as a really little person, but everybody's trying to stop it. And it's really easy to stop a small person, isn't it? But a really big person, it takes a lot more, and it just pummels through. With iodine, it's pummeling through the solvent. Fluorine is getting really held up by the solvent. But whenever the solvent's not holding anything up, fluorine can just slip on in. Iodine's just too big to be fast. Does that make sense? I mean, if you were betting people and you had someone that looked like Usain Bolt and you had to bet on like a 100-meter dash, who would you bet on, Usain Bolt or Shaq? Fluorine is Bolt, Shaq is iodine. Okay? Now if you had 10 people trying to slow them down and you had to run 10 yards, who's going to win, Shaq or Usain Bolt? It's going to be easier to hold Usain Bolt down, but Shaq can just drag the people alone, right? 10 yards. And so that's iodine. That's what's going on. The solvent, while stabilizing the carbocation, can really slow a nucleophile down. So the bigger nucleophiles can do a better job. Does that kind of make sense? So you kind of see this inverse thing going on. So I'm about to teach you one of the most marvelous tricks for this chapter. It's really going to help you. If it's elimination, what will you see on the arrow? Heat. But at this point, you've kind of been puzzled as to know if it's SN1 or SN2, right? If it's SN2, on my test that I'm about to give you in a week or so, you'll always see a polar aprotic solvent with it, unless I'm purposely trying to test something else. Okay? Let me say it this way. If I gave you this substrate, I don't really have to give you a solvent, do I? Y'all should be able to quickly say that's SN2. You have a primary alkyl halide. It's not really going to form a good carbocation, and you have a good nucleophile. That sets you up for a really good SN2 reaction to make that ether. But what if it's not so obvious? What if instead I gave you this? Let's do this. Like an amide nucleophile. Well, you'd say my substrate can do either. It can do SN1 or SN2 because it would form a secondary. It's not going to do a hydride shift to get any better. Then I would give you something to help you make your decision. You might see something like DMSO. And then you'd be like, oh, that's polar aprotic. That's going to be SN2. In which case, you would then do your inversion of configuration. And draw your product. So if polar protic solvents have the capability of hydrogen bonding, then polar aprotic solvents lack the ability to hydrogen bond, but they're still polar, okay? What are those solvents going to be? I encourage you to commit these to memory. Not the structures, but the actual names, okay? I want you to commit DMSO, dimethyl sulfoxide, that's the one I just used with that reaction. DMF, NN dimethyl formamide. Turns out that stuff's pretty dangerous. It can go right through your skin and cause liver damage. DMSO is pretty bad too. Acetone, one of our favorites from lab. Acetone is polar aprotic. Acetonitrile, remember RCN is a nitrile. Acetonitrile is the methyl version of that. Those are going to be your 4 polar aprotic solvents I'm going to use for your next test. If you see one of those, that should clue you in that I'm looking at an SN2 reaction. Okay, well, we should pretty easily be able to finish this on Friday. I'll post a quiz announcement. Wait, who sneezed? End of lecture. Okay, there it goes. It went away because y'all were staring at me. Okay, we should be able to easily finish lecture. Also, I want you to come with any E2 questions you might have from last Friday when I was absent. I'm happy to go over that. And I'll post an announcement telling you what your quiz will be over, okay? I'm going to think about it a little bit and then post it. All right, have a nice day.